All right, first video lecture for the new unit. This is Unit 2. We're talking about atoms, the building blocks of matter. So we're starting in Section 1. It's mostly the history of the idea, from philosophical idea to scientific theory. This section is going to cover the history and development of the atomic theory, all the way from Democritus to Dalton to the modern era. Your objectives for this section, you need to be able to explain the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. You also need to be able to summarize the 5 essential points of Dalton's atomic theory. And lastly, explain the relationship between Dalton's atomic theory and the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. So this is what I want you to do right now. This is a mind experiment for you to do at home, in the library, wherever you are. I want you to look around. I want you to choose an object, any object, doesn't matter. And I want you to answer this question. Can you cut that object in half? Yes or no? I'm going to assume you pick something that you can cut in half. Can you cut that half in half? Yes or no? I'm assuming that you can. Can you cut that fourth in half? Yes or no? I bet you can. Can you cut that eighth in half? I bet you can still. Can you cut that 16th in half? Now we're going to get onto a scale that maybe you can't cut it with a knife, but there's some sort of instrument that you can get, whether or not you need some sort of high military clearance to get it, but you can actually continue to cut that in half. And this is the main point. If you are cutting objects in half and continually having them, will you ever reach a point at which you can no longer cut whatever object it is in half? Yes or no? There's a fellow named Democritus who also engaged in this same mind experiment, and he concluded, yes, there is a point at which you can no longer divide matter or cut it into any smaller increments. Now, Democritus lived in the same time as Plato, as one of his peers, one of his contemporaries. He was Greek, obviously, taught in Athens, and he carried out this mind experiment that I just had you do. Note that Greek philosophers of the time didn't carry out physical experiments. They were thought to be below the level of the mind experiment. Democritus concluded that there must be a point at which you can no longer cut a sample in half, some sort of indivisible particle, and he called this particle the atom, or in Greek it would be atomos. What we say atom, this word sounds very much like the Greek word for indivisible. We have the word a, which indicates not or opposite, and then the word tomos, which refers to cutting or dividing. So not cutting, atomos, not being able to cut. And that's how the understanding of the atom stayed for about 2,000 years. Moving forward quite a bit, by the late 1700s, nearly all chemists used Democritus's definition of an element as a substance that cannot be further broken down by chemical means. It also became clear that it was the combination of these elements that resulted in the great variety of substances that we observe in nature. And there was a term that came out of this. It was called chemical reaction. The transformation of a substance or substances into one or more new substances is called a chemical reaction. You have one substance before, and you have at least one or more new substances that you didn't have before. The ancient Greeks were well known for their pursuit of truth. However, for various reasons that we will not cover here, they did not carry out experiments and take measurements nor make calculations. So it was not until the late 1700s that chemists began to carry out quantitative investigations into the nature of matter. This new attention paid to quantitative analysis led to the discovery of several of the laws that we today consider to be basic laws of chemistry. First, we have the law of conservation of mass. Second, we have the law of definite proportions. Lastly, we have the law of multiple proportions. And I will make note that this will be the subject of your quick write for this section. You will have to explain all three of these laws. Let's start with the conservation of matter. This came about, propagated by a man named Antoine Lavoisier. He was a French fellow. He came up with this idea of the law of conservation of matter, and he explained it as having a few tenets. 1. The quantity of matter does not change during a chemical reaction. You can have a chemical reaction take place, but the amount of matter that you have beforehand is the exact same amount of matter that you have afterwards. So if you have 10 grams of matter involved as reactants of a reaction, you must have 10 grams of product. No more, no less. It has to be the exact same. So that means that the sum of the masses of the products is equal to the sum of the masses of the reactants. Now, the reason that this is true, this rule has to be satisfied or observed, is because atoms are neither created nor destroyed in chemical reactions. They're simply rearranged. And because nothing is being created or destroyed, you cannot have any mass disappear or be added to the system. And what we'll learn later on is that the balanced equation is how we account for all these different chemical reactions and their masses. This is a picture representing a reaction that satisfies the law of conservation of matter. In fact, all reactions satisfy the law of conservation of matter. But here we see a molecule of methane, CH4, reacting with 2 molecules of oxygen gas, reacting to yield 1 molecule of carbon dioxide and 2 molecules of water. You'll notice that if you count the total number of hydrogens on the left side, the reactant side of the reaction, you'll notice that it's the exact same number of hydrogens on the right side of the reaction, also known as the product side. And you can do that same thing by counting the number of carbons on either side and the number of oxygens on either side, and you'll find that the numbers are exactly the same. Next law we are going to go over is the law of definite proportions. This was put forth first publicly by a man named Joseph Proust. Here's a picture of the fellow. So the law of definite proportions said that a given compound always contains elements in a certain proportion by mass. So a given compound, if you name one thing, like table salt, it will always contain elements at a certain proportion by mass, meaning that that compound, that table salt, will always be made of the same stuff because we define table salt as this particular compound. And what we find is because when we look at compounds, we can simply count the number of atoms that make up that compound or molecule. We see that atoms combine in whole number ratios, so their proportion by mass will always be the same. So here's an example. Water, H2O, is always made up of 2 atoms of hydrogen and 1 atom of oxygen. I'm sure you've seen this type of diagram of water before. H2O, we have the red ball representing oxygen and the 2 white H's representing the hydrogens. And Proust made the statement referring to mass. So let's put it in those terms. If 1 molecule of water is always made up of 2 atoms of hydrogen, we can calculate the mass of hydrogen in a water molecule. We can take hydrogen, according to your periodic table, it weighs 1.008 AMU, and there are 2 of those atoms. We'll multiply that out to yield 2.016 AMU. To do the same thing for oxygen, your periodic table tells us that the mass of an oxygen atom is 16.00 AMU, and there's only one oxygen. So doing that multiplication is pretty easy. It's going to be 16.00 AMU. And so we see that the ratio of oxygen to hydrogen in water is always 8 to 1. Okay? You can represent it as 16 to 2, but we can reduce that down to 8 to 1. And what Proust contended, his argument was, the law of definite proportions states that when you're looking at any particular molecule, in this example we're looking at water, so no matter what water you're looking at, you will always find oxygen and hydrogen occurring at a mass ratio of 8 to 1. Here's a second example. We'll take potassium chloride. Potassium chloride is even simpler. It's just one atom of potassium and one atom of chlorine. Here's a model of potassium chloride. So we have one atom of potassium that masses in at 39.10 AMU. So the mass due to potassium is 39.10 AMU. Same thing with chlorine. There's only one of them. So the mass due to the chloride ion is 35.45 AMU. So if we were to do this calculation, it would be very simple. In potassium chloride, potassium and chlorine always have a ratio of 39.10 to 35.45. Or we can reduce that down, represented as 1.10 to 1 by mass. Now, the problems that we're going to do in class, and you'll have to do on a quiz and on a test, are going to involve whole number ratios. I just wanted to include this as an example. Moving on to the law of multiple proportions. Here's where we run into my man John Dalton. Okay, here's a picture of him. And the law of multiple proportions states that when two elements combine to form more than one compound, and this is the situation, and we need to remember this situation. We can't apply this to everything that we see, but when we have two elements combine and form more than one compound, and we see that quite a bit. We see hydrogen and oxygen combine to form water, as we know, H2O, but hydrogen and oxygen also combine to form other things, like hydrogen peroxide. I'm sure you've heard of that. It's some pretty nasty stuff. Is H2O2. It's still hydrogen and oxygen, and they're combining. It's just two elements, but they end up being different compounds because they're combining in different ratios. So under those circumstances, we'll see that the ratio of the mass of one element in the first compound to its mass, the same element, in the second compound can be always expressed as a ratio of small whole numbers. So again, here's whole numbers, 1 to 3 or 2 to 5, whole number ratios. So let's look at an example. So carbon and oxygen combine, and they form, among other things, carbon monoxide and carbon dioxide. Here we got two models of those, the top one being carbon monoxide, the bottom one being carbon dioxide. Carbon here being represented by a black ball and oxygen being represented by red. So let's illustrate this idea. Let's calculate the mass due to carbon in each of these molecules, carbon monoxide and carbon dioxide. Well, according to your periodic table, that carbon weighs 12, or has a mass of 12.10 grams per mole. So mass due to carbon here is 12.01. Calculating the mass of oxygen, there's only one oxygen here, so the mass due to oxygen would be 16 grams. There's one oxygen, so 16. Calculate the mass of carbon in carbon dioxide, CO2. We still only have one carbon, so that mass is still going to be 12.01. However, here's where we get a little bit different. In carbon dioxide, there are 2 oxygens, and so the mass due to oxygen in carbon dioxide will be 32.00 grams per mole. And so what we're going to do is we're going to find the ratio of oxygen to oxygen, right? Oxygen in carbon dioxide compared to oxygen in carbon monoxide. And so what you'll do on your calculator is you'll actually divide 32.00 by 16.00, and you'll come up with a ratio of 2 to 1. So here's a practice problem for you guys to do. In the carbon compounds ethane and ethene, which are different things, we have C2H6 versus C2H4. Okay, what is the lowest whole number ratio for hydrogen atoms that react with the same number of carbon atoms? Notice it's the same number of carbon atoms here. There's always 2 carbons, but the number of hydrogens can differ. So go ahead and pause the video now and see if you can recreate the steps we just went through on the last slide. All right, here we go. We can create this table again on a test or a quiz. You're more than welcome to create this type of table to help yourself set up the problem. Hopefully, as you go through more of these problems, it becomes so intuitive that you don't need it, but you are more than welcome to do so in the meantime. So, we have a mass of carbon, we have a mass of hydrogen. Those are the only 2 elements here, and we're trying to find the ratio of the mass of hydrogen and the ratio to the ratio of the mass of hydrogen in ethene. So, let's calculate the mass of carbon in ethane. There's 2 of them, so we're multiplying 2 by the 12.01 that we find on the periodic table. Let's find the mass of carbon in ethene. It's pretty darn similar. It's 24.02 because there's still only 2 carbons here. Here's where we start getting a little bit tricky. Let's find the mass of a hydrogen in ethane. So hydrogen has a mass of 1.008 AMU. We're going to multiply that by 4 atoms. Okay, 4 atoms in, let's see. Oh, that's ethene. Ethene, 4 atoms in ethene. That's going to come in at 4.032 AMU. So I'll throw that in our table. Now for ethane, C2H6, ethane, we're going to take that same mass, 1.008 AMU, we're going to multiply that by 6 atoms. It's going to end up being 6.048 AMU. Throw that in the table. So we are simply going to take our calculators and we are going to divide 6.048 by 4.032. That is going to give us a ratio of 2 to 3. So there is more mass due to hydrogen in ethene than there is in there's more mass due to hydrogen in ethane than there is in ethene because there are more hydrogens, obviously. And we now know the ratio at which those masses occur. Okay, there are 3 units of hydrogen in ethane for every 2 units of hydrogen in ethene. All right, here is another practice problem. Please pause the video and see if you can generate an answer, and then we'll go over it together. All right, carbon reacts with oxygen to form 2 compounds as shown. In compound A, we have 2.41 grams of carbon and 3.22 grams of oxygen. In compound B, we have 6.71 grams of carbon and 17.9 grams of oxygen. And you are being asked to find the lowest whole number ratio of carbon to react with an equal mass of oxygen. So we start off, we're given 2.41 grams of carbon. I want to find the ratio to an equal mass of oxygen, and we can do that by dividing the grams of carbon by the grams of oxygen. And I'll set that up for both compounds. Notice I'm dividing my grams of carbon by the grams of oxygen, and that will make the denominator 1. It'll make it a 1. So that's the equal mass of oxygen represented as 1, and so that's going to allow my numbers to compare the amount of carbon there. So I'll actually carry out the calculations. For compound A, I have 0.748, and for compound B, I have 0.374. But that's not all. I can't forget my units. While I did divide 2.41 by 3.22, I still have those units because they didn't cancel out. So I'll have grams of carbon over grams of oxygen on both of my values. Now, what do I do with these numbers here? Okay, I have 0.748 grams of carbon per 1 gram of oxygen and 0.375 grams of carbon per 1 gram of oxygen. And again, we are being asked to compare the amount of carbon we have per equal mass of oxygen. And because our denominator is 1, okay, we're allowed to do that. These numbers that we just generated represent our masses of carbon. So what I'm going to do now to get that ratio that my answer is supposed to be, I'm going to take my smaller value and I'm going to bring it over here and divide into this larger value. So I'll end up with 0.748 divided by 0.375. Okay, throw in those units. Never forget about your units. Notice here that they'll cancel out, so they'll disappear. All right, I actually carry out this calculation, and I actually end up with a nice round number, 2 over 1. Now, in your calculator, it'll probably spit out something like 1.9978, some number that's ridiculously close to 0. That's going to happen, and that's okay. All right, that's completely okay. When you are that close to your whole number, we can go ahead and make that a 2. I included the 2 over 1 because we need to remind ourselves that the ratio, the answer that we're actually going to write down is 2 to 1. All right, your answer is going to be reported as 2 to 1 here. All right, I have one more practice for you before I'm going to let you go. Go ahead and press pause here and try this on your own. Here we have lead, and it forms 2 compounds with oxygens. We have that here, compound A. We see that it has 2.98 grams of lead and 0.461 grams of oxygen. Compound B, however, 9.89 grams of lead and 0.763 grams of oxygen. For a given mass of oxygen, right, we want to have the same mass of oxygen for both compounds here, both denominators. What is the lowest whole number mass ratio of lead in the 2 compounds? Well, we'll start by dividing my grams of lead by my grams of oxygen for both compounds, just like we did last time. Okay, now remember, I'm dividing by my grams of oxygen for both compounds so that the denominator will be 1. So my grams of oxygen will be 1, and that will create that given mass of oxygen, and that equal mass of oxygen that I need in order to be able to fairly compare my grams of lead. So bust out these calculations. I got 6.46, and I got 13.0. But remember, we got to keep these units in tow because they're going to make sure I'm doing these things correctly. So I have 13 grams of lead per 1 gram of oxygen and 6.46 grams of lead per 1 gram of oxygen. There's that equal mass of oxygen. Similarly, I'm going to take these 2 numbers here. I'm going to divide them. One thing I want to point out for this problem is you can end up getting the correct answer dividing either one by either one. But the easiest way, the shortest way to get the lowest whole number mass is to take the smaller number and divide it into a larger number. That way it'll be a number over 1. Otherwise, you're going to get a decimal. You can still get the right answer. You still will get the right answer, but it's a little bit more tedious to put that back into a whole number ratio like the question asked you. So I'm going to take this 6.46 and I'm going to divide it into 13. Okay, don't forget my units. Got to make sure I know what I'm doing here. Plug that bad boy into the calculator. I get a 1.99 over 1. Therefore, that's going to be a 2-to-1 ratio. Now, for both of these last two practice problems, the ratio did end up being 2-to-1, but realize they're not always going to be 2-to-1. They can be 2-to-5. They can be 9-to-2. Right? They can be very large, but you're going to use this process every time. Make sure you've taken good notes on this and that you've attempted the practice problems, and bring your questions to class. All right, I'll see you next period.